Imagine handing a computer a copy of Shakespeare's entire collection and just asking it to read. It's a funny image, actually. Right, because for a long, long time in the history of computer science, if you did that, the machine was basically acting as a very fast, very literal account. Yeah, exactly, a tally system. Right. It didn't know what a rose was or, what love meant. It just knew that the word rose appeared exactly 54 times and that the word sweet often happened to be sitting right next to it. It was just counting. Just counting. But today, we're going to look at the mathematical breakthrough that really changed everything. By the end of this deep dive, you, the listener, are going to understand exactly how computers transition from blindly tallying words to actually comprehending semantic meaning and context. It's quite a journey. It really is. And, spoiler alert, they do it using the elegance of continuous math. It is a profound paradigm shift. But to truly appreciate how we got here, let's anchor this to what you probably already understand about early text processing. Yeah, let's activate some of that prior knowledge. Right, so think back to the older, simpler models, things like n-grams or bag of words models. Those early systems relied on a concept called maximum likelihood estimation, or MLE, which sounds incredibly complex, but MLE is basically just a fancy term for calculating raw historical percentages, right? Pretty much, yeah. Like, if you are standing at an intersection and 8 out of the last 10 cars turned left, your maximum likelihood estimation for the next car is, well, an 80% chance it turns left. That's a perfect translation of the concept. So in those older language systems, predicting the next word in a sentence relied on that exact same conditional probability. Okay. If the model processed the phrase, the cat sat on the, yeah, it would search its training data, see that the word mat followed that specific sequence, say 80% of the time, and predict mat. Because it's literally just a giant lookup table of historical probability. Exactly. If it saw a bigger RAM, two-word combination enough times, it memorized it. But if it hadn't seen it, the probability was just 0. Okay, let's unpack this. Because to understand the brilliant solution we use in modern AI, we first need to isolate the exact point where those old n-gram models completely failed. And they failed hard. They really did. Like, why couldn't we just build a bigger lookup table? Because you run headfirst into a mathematical wall known as the Curse of Dimensionality. Ooh, the Curse of Dimensionality. Sounds ominous. It is, for a computer at least. The language is just incredibly expansive. Let's say your vocabulary is 100,000 words. Okay, pretty standard. If you want to track 2-word combinations, that's 10 billion possible pairs. Wow, 10 billion. Right, and if you want to look at a slightly longer sequence to get better context, say 3 words, you are suddenly looking at 1 quadrillion possible combinations. 1 quadrillion. And I mean, most of those combinations will literally never appear in any training data, ever. Nobody is writing the sentence, the xylophone melted gracefully. Precisely the issue. So when the anagram model encounters a sentence it has never explicitly read before, it just freezes. It panics. Yeah, it has no historical percentage to draw from. It assigns the sequence a probability of 0, and the system crashes. So what did they do? Well, early computer scientists tried to fix this using smoothing algorithms. They would essentially skim a tiny fraction of probability mass from the words they did know and distribute it to the unseen combinations just to keep the system running. But that feels like, I don't know, a statistical band-aid. Because it is. The model wasn't actually learning anything about the language. It had 0 ability to generalize. Like it couldn't look at the dog rested on the rug and realize it is semantically identical to the cat sat on the mat. Because the words are different. Exactly. To a counting model, those are completely unrelated alien universes because the individual tokens just don't match. So to force the computer to recognize individual words, early computer scientists tried a workaround called one-hot encoding. Let me try to visualize this for you, the listener. Please do, the visual helps a lot here. Imagine a giant, incredibly sparse warehouse of a filing cabinet. You have that vocabulary of 100,000 words, so you build a cabinet with 100,000 drawers. It's a big cabinet, a massive cabinet. And every single word gets its own dedicated drawer. But inside that drawer, there's only a single piece of paper with the number 1 on it. Every other drawer in the entire cabinet gets a 0. and that creates a highly specific mathematical vector for every word. Right. So the word wolf is represented as this massive sparse array. It's like bracket 0, comma 0, comma 0, and then way down the line at drawer number 42,000, a single one, and then 50,000 more zeros. Just one solitary one in a vast sea of nothingness. Exactly. And this is where we need to explicitly address a very common misconception. Because when you first hear about one-hot encoding, it is tempting to think that because the computer now has a unique mathematical identifier for the word wolf, it has somehow captured the identity of a wolf. But hasn't at all. It hasn't, not even a little. It's really just a barcode. And, a barcode tells you an item rings up as $4.99 at the register, but it contains zero information about whether that item is a bunch of bananas or a heavy-duty blender. That analogy hits the nail on the head. A one-hot vector cannot measure semantic similarity at all, right? If the ultimate goal of language modeling is to relate concepts to one another, one-hot encoding fails spectacularly. In that system, the mathematical distance between the vector for wolf and the vector for dog is the exact same as the distance between wolf and Starbucks. Oh, wow. So they're all just equally far apart. Yes. Every single word is equidistant from every other word. They are perfectly isolated orthogonal points floating in a vacuum. There's absolutely no context. Which means we are stuck again. Like, if one-hot encoding leaves us with these rigid data points, how do we build a system that can actually compare tokens in a meaningful semantic way? We abandon the sparse warehouse entirely and we move into continuous space. Exactly, continuous space. This is the massive breakthrough driven by researchers like Thomas Mikolov and his colleagues around 2013. They proposed a radical shift. What if we stop using a vocabulary-sized vector filled with 99,000 useless zeros and instead map words into a continuous vector of a predefined, much smaller dimensionality? So instead of 100,000 drawers, we shrank the cabinet down to, say, 128 drawers, or 256. We compress the space significantly. But the critical difference isn't just the size. Instead of just holding a 1 or a 0, every single drawer, every dimension in this new vector holds a continuous floating point number, like a highly specific decimal. Let's make this math tangible. In this new continuous space, the word wolf isn't a single one anymore. It becomes this rich, complex signature of decimals. Right? It looks like this 0.1203, comma 0.829, comma negative 0.033, and so on across all 128 dimensions. Meanwhile, the word Starbucks becomes a completely different signature, like negative 0.03, 1.434, 0.21, and predator is 1.320, negative 0.813. You get the idea. You've just described a dense word embedding. But wait, let me push back on this because I'm thinking about the sheer processing power here. Calculating the distance of 1 billion words across 128 different mathematical planes simultaneously, that seems impossibly computationally heavy compared to just checking a single one in a drawer. Wouldn't this crash the computer? You would think so, but it's actually the opposite, due to how computers handle matrix multiplication. Really? Yeah. Sparse matrices, those one-hot vectors with 99,000 zeros, are incredibly inefficient. The computer wastes enormous amounts of memory just storing and multiplying by 0 over and over. Oh, because anything times 0 is just 0. It's doing pointless math. Exactly. A dense vector of 128 continuous floats, on the other hand, is a tightly packed block of data. Modern processors, especially GPUs, are heavily optimized to multiply dense flocks of floats at lightning speed. Okay, so the hardware can actually handle it better. But what do those 128 numbers actually represent? Like, if dimension number 12 is a high positive number for wolf and dog, does dimension 12 mean fluffiness? Do human programmers sit down and label these dimensions? No, and that is actually the most beautiful part of this whole architecture. It is entirely unsupervised. Completely unsupervised. Completely. The dimensions are abstract. We don't explicitly know what dimension 12 represents. We just know that the neural network, during its training phase, decides that dimension 12 is highly relevant for separating animals from vehicles. So how does the network figure that out? What is the actual mechanism that nudges these decimals until wolf and dog end up with similar signatures? It happens through a process called backpropagation. Let's walk through a sort of micro-simulation of how it learns. Okay, let's do it. Imagine the neural network is reading a sentence and trying to predict the next word. It guesses the word rug, but it checks the actual text and the real word was mat. So it made a mistake. Right, but in continuous math, mistakes are highly valuable. The computer calculates the exact mathematical difference between its guess, rug, and the reality, mat. This difference is called the error, or the loss. Okay, I follow. The network then takes that error and mathematically fires it backwards through the system. This backward signal calculates a gradient, basically a set of directional instructions, like a correction. Exactly. It tells the vector format, hey, your float values in dimension 42 need to shift down by 0.01, and your values in dimension 19 need to shift up by 0.05, so you act more like RUD next time. Wow. So every single time it guesses wrong, it mathematically nudges the floats. And if you do that over billions of words, iterating over and over, words that appear in similar contexts are literally pushed and pulled through this 128-dimensional space until they physically cluster together. Exactly. The errors force the geometry to perfectly align with semantic meaning. Let's step back for a metacognitive prompt here. Why does this matter to you, the listener? Because now that we have these words floating around as precise coordinates in a 128-dimensional space, we have a way to mathematically prove that the computer understands their relationships. Yes, we can just measure the physical distance between them. Right. We use metrics like Euclidean distance, which measures the straight line between 2 points in space, or cosine similarity, which measures the angle between their vectors. Regardless of the metric, when you map this out visually, you get these breathtaking 3D graphs that look like constellations of stars. And in these constellations, you start seeing parallel trajectories that just blow my mind. For example, if you draw a line in this geometric space from the word man to the word woman, that exact spatial arrow perfectly mirrors the distance and direction between the word king and the word queen. It's incredible. The model has captured the abstract concept of gender as a geometric trajectory without ever being explicitly programmed to understand what gender is. And it does it for grammar too. The trajectory from walking to walked is perfectly parallel to the trajectory from swimming to swam. It even learns geography. It really does. The spatial relationship connecting Russia to Moscow is identical to the one connecting Japan to Tokyo. Which brings us to vector composition. Because these relationships are consistent, we can actually perform semantic algebra. Semantic algebra, doing math with words. We can do math with concepts. Let's walk through a complete example, step by step, to see this in action. We are going to calculate an equation. So you start with the mathematical coordinates for the word Einstein. Okay, I have my starting point in the space and at Einstein. From those coordinates, you mathematically subtract the vector for scientist. Think about what that means. You are removing the semantic direction of being a scientist from Einstein. Okay. What you're left with is a spatial location that represents his raw essence prominence, historical genius, mid-20th century weight, but stripped entirely of the scientific discipline. That is just wild to visualize. A genius without science. Then, to that abstract location, you add the vector for Picasso. You are taking that raw historical genius and steering it directly into the realm of visual art. Okay. When you look at the final coordinates you land on, you ask the system, what word is physically closest to this point in space? The output is the word painter. Einstein minus scientist plus Picasso equals painter. It works. Okay, before moving on, try this yourself, listeners. Let's do a formative check-in. Based on the rules of vector math we just learned, if you take the vector for Miami, you subtract the vector for Florida, and you add the vector for Maryland, where do you think you end up in the vector space? It's a great test of the concept. Take a second to think about it. Miami minus Florida plus Maryland. If you guessed Baltimore, you nailed it. You removed the specific state context of Florida, isolated the major metropolitan city essence, and applied it geographically to Maryland. Boom, Baltimore. And that outcome is the definitive proof, but the model isn't just memorizing lookup tables anymore. It has deeply internalized the abstract relationship between cities and their states as a fundamental geometry. But this mapping process doesn't just happen by magic. If we want the AI to cluster king and queen, we have to train it. What is the mathematical engine actually assigning these probabilities? The foundational architecture for this comes from a landmark 2003 paper by Yoshua Bengio and his colleagues. They formalized how a neural network language model, or NNLM, could learn these embeddings. How did they do it? They designed a function, let's call it function G, that is parameterized with learnable weights. The job of function G is to take a continuous representation and output a normalized probability distribution over the entire vocabulary. You mentioned a normalized distribution. Is that where the term softmax comes in? Because I see that thrown around a lot in these discussions. Yes, exactly. Think of softmax like an audio soundboard. When the neural network makes its raw guesses about what word comes next, it outputs a bunch of messy, unconstrained numbers. Maybe a 45 for mat, a -12 for xylophone, and a 300 for rug. Just noise, basically, right? Softmax is a mathematical filter. It takes all those messy raw scores and squashes them into clean, readable percentages that will always add up to exactly 100%. It forces the model to place its bets definitively. Okay, that makes sense. It cleans up the math. But let me push back on a sequence. If it's a language model trying to predict words, is it reading backward like those old anagrams, or is it reading forward? That depends entirely on the specific training architecture you choose. In 2014, Tomas Mikolov introduced two highly specific ways to train these vectors. The first is called CBOW, which stands for Continuous Bag of Words. How does CBW read the sentence? In CBW, the model tries to predict a single target word from its surrounding context. Think of it like a redacted spy document. Ooh, I like that analogy. If you read the sentence, "The president boarded the blank to fly to Paris," you don't actually need the strict sequential order of the surrounding words to know that the missing word is plane. Right, context words, president, fly, Paris, they all pool together to inform the center word. It's a bag of words because the historical order doesn't dictate the prediction. Got it. The context points inward to the target. So what's the second model? The second model is the exact inverse. It's called skipgram. Instead of using the surrounding context to predict the blank space in the middle, skipgram gives you the middle word and forces you to predict the context around it. Wait, so using the spy document analogy, skipgram just gives you the word plane and asks you to somehow guess that the surrounding words are president and Paris. That seems much harder. It is mathematically harder, which is actually why skipgram often produces higher quality embeddings for rare words. The architecture sets a range called K, which defines how far into the past and future it should look. Okay, so if K is 2, it takes the word plane and tries to predict the two words before it and the two words after it. Wow. And by forcing the neural network to play these relentless prediction games, either CBOW or skipgram over billions of words, you generate those constant errors. And those errors are what drive the backpropagation, constantly fine-tuning the 128 dimensions until the semantic map is perfect. So to bring this all together and summarize our journey, we started in a world of discrete, isolated n-grams, systems that just blindly counted history. Then we explored sparse one-hot encodings, which gave words unique IDs, but left them stranded as isolated barcodes with no semantic relationships. Right, the giant warehouse. Exactly. And finally, we crossed the threshold into rich, trainable, continuous vectors. By mapping words into an n-dimensional space and updating them through backpropagation, we allowed the computer to understand context via spatial distance. The computer stopped acting like an accountant tallying the word rose, and finally learned that rose sits right next to flower, red, and romance. It's just so cool. It is. And it's vital to transfer this knowledge to what's happening in the world right now. The massive large language models making headlines today, the ones passing bar exams and writing code. Yeah, the ones everyone is talking about. They are built entirely on the shoulders of these dense, continuous word embeddings. This geometric continuous math is the absolute bedrock of how machines process human language today. Okay, here's where it gets really interesting, and it leaves you with something profound to explore on your own after this deep dive. We spent this entire time talking about how we've mathematically mapped human language into this 128-dimensional geometric space. Right. But if meaning is just geometry, what about the empty space? In a continuous mathematical map, there are countless coordinates between our words that don't map to any English word currently in existence. Oh, that's a fascinating thought. Does that mean the AI has built a space for concepts, emotions, or ideas that humans haven't even invented words for yet? Are there alien geometries of thought sitting quietly inside these models just waiting for us to find a translation? That is a staggering implication of continuous mathematics. It really makes you think. Thanks for diving deep with us today. Keep questioning the space between the words, and we'll catch you next time.